All right, everyone. This video is going to cover, by reference, chapter 10.3 in the textbook. As you might remember, there was some jumps here and there. We're going to continue on with acids and bases, specifically stoichiometry of acids and bases, with an explanation of this thing called titration. So you also find that if you look at the textbook, chapter 10.3 is the end of chapter 10. Why is that? Simply put, if you've been practicing with stoichiometry all this time, you will find that the calculations we do are virtually the same. As I was saying to some students, stoichiometry is up until now sort of like a larger umbrella. Okay, stoichiometry, and until now, it's not like it's a new concept. If you know how to do the calculations for stoichiometry, all you have to do is sort of pay attention to how stoichiometries might be slightly different when we're talking about mass of solids, when we're talking about solutions, so, aqueous solutions, when we might talk about gases, in this case, when we talk about acids and bases, so on and so forth. But they're all under the stoichiometry umbrella. So again, hope you've been practicing, hope you've been keeping up. If you have a textbook with you, I highly encourage you to pause the video and get that open. Grab a paper and pencil and copy stuff down. I'm going to explain to you how stoichiometry is similar and how it's slightly different with acids and bases. And as I do so, I may drop a scientific term called titration on you. Long story short, titration is a science term where you are in a lab experiment setting, in a laboratory experiment setting, you are trying to do a perfectly balanced neutralization reaction. Okay, so titration is a neutralization reaction in a lab. That's it. Okay, so don't be scared about it. Then we'll try some text sample questions from the textbook with my little spin-off on it, and then homework, of course. Your homework being speed read chapter 10.3, which starts at page 476. Then try numbers 1 to 3. The answers are already embedded in the question. And then page 485, try the section questions. The whole answer should be in the back of the textbook. All right, here we go. Explanation. If you go back to your grade 10 knowledge, you may remember a bunch of different types of reactions you had to sort of memorize. That's single displacement, double displacement, synthesis, decomposition. And then off of the double displacement reaction, there was a sort of side category called neutralization. When you are doing stoichiometry of acids and bases, what are you trying to do with acids and bases to begin with? We are trying to not balance, but perfectly neutralize the acid component, which is a hydrogen ion, and the base component, which is a hydroxide ion, right? Perfectly neutralize H plus and OH minus. What does that mean? We want to perfectly match the number of moles of H and OH in a reaction. How do we do that? Well, in a lab, we perform this thing called titration, a very, very, very detail-oriented, very careful, you have to be really careful with your hands, a procedure where you're dripping little bits of acid or base to match the number of base or acid, whatever we're measuring. I'll get more into that. What do I mean by perfectly matching the number of moles? Well, this is what I mean. If I have HCl plus NaOH, and I know as a double displacement reaction, I'm going to have NaCl plus H2O, the coefficient is going to be 1, 1, 1, and 1. So let's turn it into a chart. If I have 0.5 moles of HCl, that also means, using your calculations, I also have 0.50 moles of hydrogen ions when HCl dissociates. So how many moles of NaOH do I need for it to be perfectly neutralized? Well, to fully or perfectly neutralize would mean we have exactly enough of both reactants so that they both run out and none is left over. So let me write that in, okay? To fully neutralize would mean to perform a reaction without any acid or base reactant left over. And does that make sense? I hope it does. If we're talking about limiting reagents here, if there is an existence of a limiting reagent, we haven't neutralized it. Think about it. If NaOH was the limiting reagent, that means I would have HCl as excess, which means I have H plus as excess. That means my solution is still acidic. We haven't completed the reaction. Let's keep moving. If HCl was a limiting reagent, that means NaOH is excess, which means it's still basic. See what I'm getting at? Titration is a procedure to make sure we fully neutralize something. All right. Yeah. So on paper we just call it stoic, but in a lab it's called titration, right? Because we're actually performing it to make sure it's real. So what does titration look like? Let's clear this first. Okay, in 3, 2, 1. Titration. Titration in terms of a lab apparatus is very, very simple, but if it's the first time you're seeing this, then yeah, I could see it being a little bit more stressful. So the idea is this. Inside here, we have something called an analyte. Why? Because we're going to analyze it. Ta-da! It's actually some, by definition, some known volume, because you can measure it out, of an unknown concentration of typically an acid. So think about it, like the best example I can give you is forensics. Let's pretend that, next to a dead body, they detected some kind of liquid. They're not sure if it's poison. They're not sure if it's acid. So the forensics, investigators or whoever sort of shows up at the crime scene, collects a bunch of samples, takes a small sample. Let's pretend like, 10 milliliters is enough, right? They put it in a Erlenmeyer flask, right? And even though they don't know if it's a very strong or weak or dangerous acid, they will start dripping titrant into it. So we are titrating with a titrant. What is a titrant? It is some known concentration of a base. And let's pretend I start with 0 dripped in, and then this continues to drip in like an IV until I used about like 20 mils difference, right? Then I know the concentration, I know the volume. So I know the concentration of the base. I know the volume of the base that I put in. So titrate will be, let's pretend I put in NaOH, okay? If I know the concentration of the base, NaOH, and I know the volume of the base, NaOH, that I used, then using C equals N over V, or N equals C times V, I can calculate how many moles of the base that I put in, which means I know how many moles of hydroxide that I put in. On the flip side, let's do an acid. This acid, the analyte, I know what volume of the acid I have because I just told you, you can measure that out. But as I said before, I don't know what the concentration of the acid is, right? That's a big X because, well, it's a mystery acid. I don't know how strong it is. However, if I know that I have titrated, if I have fully neutralized the solution of acid, then I know how many moles of hydrogen ions I have, right? Go back to the previous section of my video. We need the amount of moles to be equal to the amount of moles, of hydroxide to equal the amount of moles of hydrogen. That's why we call it neutralization. Because if you have an equal amount, we produce that same number of water molecules. So if you have number of moles, then you have that means we can, using C equals N over phi, calculate what the concentration of that acid is and determine whether that's harmful or not. Get what I'm saying? Hope so. Go back and try watching the video again to see if you understand what titration is. The reason why I'm going into so much depth as to what that looks like is because although we can't perform a titration together, I may give you some kind of simulation or some kind of dry lab that gets you to sort of simulate in your head. So there's another way to practice your imagination skills, I guess. Right now, I'm going to go into our sample question straight from chapter 10.3, page 482. But I'm going to do my own spin to it to give you a better idea of how we do the calculations for, do the stoichiometry for acids and bases. And that is even for, titrations. This is the same kind of calculations. Here's my spin-off. So sample question, page 482, but with my rendition. 10.0 milliliters of an unknown concentration of sulfuric acid solution was titrated, which means perfectly neutralized, with 12.42 milliliters of 0.100 molar NaOH. What is the concentration of the acid? Before I move on, something I forgot to mention about titration. How do you know if you perfectly neutralize it with your human eyes? We can't look at things microscopically or atomically. Well, we actually add something called an indicator in there. And up until now, I believe you are aware of indicators like litmus and also indicators like phenolphthalein. Some other common indicators are bromothymol blue. What else is there? There's a lot. I just doesn't come to mind. Anyways, yeah. And so when the color changes of that indicator, we know that the number of hydrogen and hydroxide are equal. All right, so let's do this. I'm going to start off with the equation. The reason why is because unlike my previous example where I wrote an equation, this one, the acid and the base is in a 1:2 ratio. The mole ratio is 1:2 because this acid provides 2 hydrogens while this base only provides 1 hydroxide. Let me just quickly finish, and then each reaction gives me 2 waters. Let's continue. Mass, molar mass, moles, N over V equals C. Okay, I don't know how many of this actually need, but here we go. Let's see. I have 0.01 liter of the acid. I used 0.01242 liters, an acid of a concentration of 0.100 molar. What is the concentration of this? Well, here's how it works. Just like before, you are looking at stoichiometry and the idea, because of the word perfectly neutralized or the word titrated, it's essentially saying that the number of moles of my hydroxide is going to be perfectly balanced with the number of moles of sulfuric acid. And by perfectly balanced, I don't necessarily mean equal, I mean in a proper 1-to-2 ratio. Because if I have a 1-to-2 ratio, then none of the acid, none of the base is going to be remaining after all the reactants are used up. Okay, I don't mean exactly equal in number, I mean there is a perfect ratio between the two. So this is my process. I'm going to do this, and then I'm going to assume that in a 1-to-2 ratio, we have just the right amount of moles of sulfuric acid, and using that, I'm going to calculate the concentration. All right, so let's see if I can color coordinate this. I'm going to do this as number 1. Blue, the number of moles of NaOH, or rather, you can say that the number of moles of OH is going to be concentration times volume. 0.01242 times 0.100 is going to be 0.001242 moles. All right, next comes, let's write it in green, this arrow. The mole ratio, the number of moles of H2SO4 to the number of moles of NaOH should be 1-to-2. Well, the number of moles of NaOH is 0.001242. So how many moles of sulfuric acid do I have? Cross multiplying, X is going to be 0.000621 moles. So this is 0.000621. Okay, nice. Final step, that's going to be in red. I'm going to calculate that. If the number of moles is 0.000621, the number of the volume is 0.0100, concentration being N over V is going to be 0.000621 divided by 0.0100. And that means 0.121 moles. Sig figs, 3, 3, 4, 3. Okay, that means the concentration of the acid is 0.0621 moles per liter. Done. What do you think? Doesn't seem that bad, right? Acid and base, again, all you're doing differently from before is introducing the word titrated, which means the mole ratio has to be perfectly satisfied. There is no limiting reagent. All right, let's take a look at sample problem 2. I'm going to read it very carefully. You know what? I'm going to type it out. If you want to clear the screen or get another piece of paper or open up your textbook, now is the time. Page 483. Sample question 2. A 0.306 gram mass of potassium hydrogen phthalate, which is KHC8H4O4, wow, or KHP, is dissolved in 50 milliliters of water. This solution is titrated. A sodium hydroxide solution of unknown concentration. It is determined that 14.080 milliliters of the sodium hydroxide solution is needed to titrate the potassium hydrogen phthalate sample to the endpoint at which phenolphthalein indicator changes color. Calculate the amount concentration of the sodium hydroxide solution. That was really long. And there's a lot of information there. Okay, let's do that one more time. I have a certain mass of this gigantic molecule. it's dissolved in 50 milliliters of water, okay? And please note, some people have asked me, isn't that technically wrong in calculating the concentration of something? Calculating the concentration, isn't it the number of moles divided by the volume of the solution, not the volume of the water? You are correct, absolutely correct. But most textbooks typically interchange the volume of water, that's the volume of solvent, with the volume of solution when it comes to concentration. In a lab setting, most of the time, it's negligible and not a big deal. In grade 12, when quantity becomes more important and makes a larger impact on the final calculation, you will see, and you will probably calculate and earn your right to make a assumption that it doesn't make a difference in the volume. Okay? What I'm trying to say is, don't worry too much. Just use this as the volume of the solution, right? This solution is titrated, in other words, fully neutralized with a sodium hydroxide solution of unknown concentration. It is determined that 14.80 milliliters of it is used until it changes color. That's basically saying that, again, it's titrated and the number of moles of hydrogen and hydroxide are going to be equal, at least in the grade 11 level. Calculate the amount concentration of the sodium hydroxide solution. Wow, what a mouthful. As usual, I'm going to start with KHC8H4O4 plus sodium OH gives me, I'm going to assume that is going to be my acid, because typically that is, that's usually how they like to express it. Am I correct? That is correct. So you can assume that this is a funky acid that only gives one hydrogen plus, okay? So you could, yeah. Anyways, if I were to neutralize it, I get water plus this funny looking NaKC8H484. Yeah, I know. The textbook is just being extra, okay? But bear with me. This is going to be good practice for you anyways. All right, so there is my reaction. Here we go. Mass, molar mass, number of moles, V, N divided by V equals C. All right, I have 0.306 grams of this. It's dissolved in 0.05 liters. It creates 0.05 liters of solution. It is titrated, where I do not know the concentration of hydroxide. I would use 0.01480 liters of it until it's perfectly neutralized. Calculate the concentration of sodium hydroxide. This is what I'm looking for. Woo! All right, I'm gonna give you, or you can pause the video, but I'm gonna give you 3 seconds to sort of plan out your mode of attack, your strategy, or not. Okay, in 3, 2, 1. Having the mass of, okay, so the end goal is I need to make sure that I have a balanced number of hydrogens and hydroxides. Knowing that it gives, every single molecule of this phthalate gives one hydrogen, it's going to essentially be a 1-to-1 ratio. Okay, so this is my end goal. Why? Well, I'll explain in just a second. I'm going to use mass, and you should be able to calculate molar mass using this and our periodic table. I'm going to use that to calculate the number of moles. Okay? Yeah. And from there, using my mole ratio, I should be able to figure out how many moles of hydroxide was used, therefore how many moles of sodium hydroxide was necessary. And if I have the number of moles and I have the volume, I can calculate what the original concentration was. Does that look weird? Some of you might be asking, whoa, 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 whoa. Why did the textbook give me this in the first place? Well, don't worry about it. Maybe that's why they gave it to you, right? It's dissolved in 50 milliliters of water. They didn't say solution. So technically, if you want it to be, again, technical, 0.05 is actually the incorrect number to put in here. Depending on the textbook, again, I keep on saying that they sometimes use it interchangeably. But right now, we don't even have to go in that direction. We don't need it. Let's follow those red arrows, shall we? All right, erasing, erasing, erasing. All right, let's do it. The molar mass of KHC8H4O4, see if I remember this. Potassium should be 40.08. Don't quote me. 39.1. My bad. 39.1 plus 8 carbons, which is 12. Man, I'm having brain farts here. 12.01. Okay. Plus 5 hydrogens, 1.01, plus 4 oxygens, which is 16. The molar mass of the phthalate is 204.23. What is that? Okay. Mass, 0.306 grams. Molar mass is 204.23 grams per mole. The number of moles being moles per over molar mass, 0.306 divided by that is 0.00149831 moles, which is rounded to 3 sig figs, 0.00150 moles. That's a nice number. Okay, next let's use a different color. This is my next goal. By mole ratio, I know that the number of moles of the KHP, is that the acronym that they use? KHP, okay, to the number of NaOH is going to be 1 to 1. That means if I have 0.00105 moles, then I would have 0.00105 moles of NaOH. Sorry, 150. Have I been saying 105? My goodness. It's been a long night. Lastly, it's final straw. To find the concentration, I know it's going to be moles divided by a volume, 0.00150 mole divided by 0.01480 liters. That's going to be 0.10135, which is about 3 decimal places. A concentration, so the concentration of sodium hydroxide is 0.101 moles per liter. That is stoichiometry for acids and bases. We are always trying to make the acid and base equal. What does that mean? You have to make sure to check how many hydrogens and how many hydroxides each molecule is donating or is making available, right? So that's basically it. Stoichiometry, please make sure it's not about limiting reagents. It is about trying to make the two amounts of each reactant perfectly matching so that no acid or no base, no H or no OH is left over. Please make sure that if I gave you something like NaOH with phosphoric acid, look at how many hydrogens are going to be produced. You can bet that you're going to need a 1 to 3 ratio, because this one gives 3 at a time, whereas this one only gives 1. These are the kinds of things you just might have to watch out for, and I guarantee you're going to encounter some questions like that from the homework. But I think I've spent enough of your time trying to go through some stoichiometry questions with you. please be wary. This type of calculation is what is necessary if and when I give you a dry lab for titration. So a couple of new words. View the video again if you need to. There's a lot to consider at once when you're dealing with stoichiometry, especially when you recognize it's an acid versus a base. Nothing else I can say. Please practice. Try the questions I have assigned. If you're a little confused on something, you know you can always email me. And if I think it's going to help the class, I will post a video response to your question. All right. Do your very best. And yeah, congratulations on finishing chapter 10. We're going to continue some of this next week. Bye.